So now we've defined Bayesian games, both in normal form and extensive form. And in the last video, we solved a Bayesian game by somewhat informal means, by iterated deletion of dominated strategies. In this video, we're going to see how to modify the definition of Nash equilibrium in order to make it appropriate for Bayesian games. So this leads to a solution concept called Bayesian Nash equilibrium. And this is a solution concept in which Bayesian updating is built in. Okay, so Bayesian games are kind of subtle. You need to think very carefully about what is beliefs and what is knowledge of players at different points in time. So during the play of a Bayesian game, information is revealed over time. So initially, when the game starts, no types are known. There is only the prior, which all players share. And then there's an intermediate point, which is where each player learns their own type, but still only has beliefs about the other players, and that's when Bayesian updating happens. And then in the end of the game, payoffs are awarded, at which point you can think of the types as all being revealed. So traditionally, because economists love showing off with Latin, these three phases are called ex ante, ex interim, and ex post. So we can talk about expected payoffs relative to each of these kind of knowledge states, or so the fancy way of saying that is epistemic states. The easiest one to define is the ex post expected payoff, which is the one where all types have been revealed. So this is a function of all of the strategies and all of the types. And so this is kind of, we take the probability that, so for each possible combination of moves, so I've defined this for mixed strategies. So for every possible combination of moves, we take the probability that that combination of moves is played, which is because the mixed strategies are independent of each other. This is the probability of, so the probability product of the probabilities that each strategy sends that type to that move. And then we can plug this into the actual payoff function, which is a function of moves and types. Okay. Now, the most important one is ex interim expected payoffs. And this is because of the general principle that a rational player should maximize their expected payoff with respect to the knowledge that they had at the time in which they made the decision. That's a very important principle. And actually, this is a kind of important principle for real life as well. And once you realize this and you watch the news or whatever, you start to see this fallacy all the time of people being criticized for making decisions based on information that was not available to them at the time when they made the decision. So the kind of correct decision making, whatever that means, is optimizes expected payoffs with respect to the decision maker's knowledge at the time at which they made the decision, not the time at which payoffs are awarded, which is different. So after making the decision, more information can become revealed. So what this means is, yeah, the ex interim expected utility is kind of the right one. So this is given by something like this, where, so this is a function of all of the strategies, but player I's expected payoff is given only by player I's type. And so what we do is we have to sum over all of the types that everybody else could have and weight by the posterior probability that those players have those types given player I's type. So so this term here, this conditional probability, we calculate using Bayes' law in general. So there are two extreme cases of this. One is where the types are perfectly correlated, and one where the types are independent. So in the case where the types are independent, the conditional probability given player I's type is equal to the prior probability. So because when they're independent, learning your own type reveals no new information about about the other player's type, so it stays the same. The other extreme case is where the types are completely correlated. So say, for example, all the types have to be equal with probability 1, then that means that after learning your own type, your posterior belief about your opponent's type collapses to a point distribution where you know with probability 1 that they have some type. That's the extreme case of completely correlated priors. Okay, so now we can define what it means for a strategy profile to be a Bayesian Nash equilibrium. And this is a little bit complicated. So we have an optimality condition that says that for every player, and also for every type that that player could have with positive probability, so let's say kind of every possible state of the world, that player's strategy is going to maximize. So that player's strategy takes their type to a move, and so that move must maximize the X interim expected payoff with respect to knowing that type. That is to say, so the move that playwright strategy plays, if they have this type, must be maximal among all of the deviations to other moves they could do of the X interim expected utility. So if we expand this out, it turns into this very scary looking formula. So here we kind of take the probability that all of the other players choose any other combination of moves, whereas player in question, is sticking to their particular deviation, and then we maximize over those deviations. So the key thing is that previously we've generally had, well, so for normal form games, we've had an optimality condition for every player saying that their strategies are optimal. For extensive form games, we've often, so for example, for subgame perfect equilibrium, we have an optimality condition for every player and also every state of the game, like every node of the tree that player could be in, or every information set. Bayesian Nash equilibrium is a bit like that. We think of types as like states of the world, and then we say we have an optimality condition for every player and every state that player could be in, which is every type that they could have. Okay. So let's go back to the example that we had in the previous video, which is the modified Nash equilibrium, where when player 1 has type 2, they get a -2 payoff for defecting. So we can calculate the expected payoffs. So in this case, player 2 only has one type, and we have independence. So we have player 1's type and player 2's type are independent for the prior. So what that means is no Bayesian updating happens. We'll say if player 1 has type 2, then the expected payoffs for all possible deviations are, if player 1 chose to defect in type 1, we would be in this situation, they'd get a payoff of 1. If they cooperated in type 1, they'd get a payoff of 0. And so yeah, no Bayesian updating is happening. So that is to say, player one knows with probability 1, no matter what, that player 2 has type 1. And we see that, so defecting is optimal for player 1 in state 1. And then similarly, in state 2, if player 1 defects, they get a payoff, expected payoff of -1, and if they cooperate, they get an expected payoff of 0. So that means that in state 2, player 1 playing cooperates is optimal. So for player 2 only has one type, which is type 1, and we see if they defect, then the expected payoff is this. So here the expectation over, so player 2's posterior over player 1's type after player 2 revealing that they're type 1 is the same as their prior, because player 2 is always type 1. So learning it, they know as a prior that they're type 2 with type 1 with probability 1. So learning that doesn't give them any new information. There is no Bayesian updating. So in the end, we get this, and we learn that player 2 strategy for, and implicitly this is sigma 2 of type 1, is d for every value of mu.